was built and then didn't change over time. So it's just there in your brains and then doesn't change. But it turns out that from human neuroimaging studies, we recently found that when humans learn to do new motor tasks like learning to juggle, learning to play the piano, they actually have very dramatic changes from imaging in their white matter. So white matter, these are the axonal tracks that are crossing from one hemisphere to the other, going long distances. They're called white because they're coated in myelin. So there's so much myelin in the white matter of your brain that it's called white matter. So this was a puzzle. It looked like instead of changes in the gray matter in the neurons, there's actually changes happening in the myelin. And so Michel Mange at Stanford did this really clever experiment. So this is using a tool called optogenetics, where you can stimulate precise neurons in vivo in an animal, in this case in a mouse. So I'm going to play the movie. So this mouse, okay. The mouse is just hanging out, and then you'll see a blue light. I don't know if you can see that, but right now there's a blue light that's exciting neurons in the mouse is turning to the left, so in the right hemisphere of the mouse's motor cortex. And only when that blue light is being shined, the mouse is forced to run around in circles. So play that one more time just so you can capture this. There we go. Light is on, and the mouse is running around in circles because we're driving neuronal activity specifically in that set of neurons that drives motion. And this has been known for a little while, but what was so exciting was that Michel Mange's lab found that in response to this neuronal activity, stimulated neuronal activity, there's a very, very rapid and very, very strong induction of oligodendrocyte formation and creation of new myelin around axons. So now a number of labs around the world have reproduced this with different techniques. And the idea is basically that in response to neuronal activity, not only do you form and strengthen new synapses, but you also promote the formation and potentially the remodeling of myelin around the axons. And so if you just take a step back, this actually makes a lot of sense. So if you think of your brain as a circuit, what can you do to change the properties of that circuit? You can change the connections of the circuit and the strength of those connections. You can change the likelihood that a given neuron will fire an action potential in response to a stimulus, and you can change the speed at which that action potential propagates. So that's the idea now, is that myelin is actually able to, on the fly, dynamically change in response to neuronal activity to help us build a functional nervous system. And so a lot of open questions here. We don't know what the signals that are coming from the neurons are. We don't know whether this is actually happening in real time in the human brain, and whether it's actually truly important for plasticity and learning. And this is some questions that my lab is building on to try to figure out over the next couple of years. Okay, so putting this all together, what I hope that convinced you is that we shouldn't call it neuroscience, this shouldn't be SFM, it should be neuroglial science, essentially even glial science. I'm pushing my luck here. So glia are really important for the development of the nervous system, its proper function. They're involved in many diseases. I didn't have time to tell you about all the diseases that glia potentially play a role in. Oligodendrocytes make myelin, astrocytes help build synapses that are important for survival of neurons. Microglia respond to injury and are the immune cells of the brain. And all of these guys are probably really important for diseases. So with that, I want to ask one last open question. What roles of glia are still undiscovered? I have a strong feeling that we still don't know everything about what glia do because we've only really been studying them for the last 2 decades. So here's a paper that if anyone's interested, you can actually email me. It's zucchero@stanford.edu. I can get you access to this paper if you can't find it or don't have institutional access. This is a great recent review on what glia do by a couple of great people in the field. And with that, I'd like to thank my lab. Best job in the world being a PI, professor, mentoring amazing young scientists and helping them go on to become scientists, hopefully soon. My funding sources, and you all for your attention and the opportunity to speak. Thank you.
Thank you so much to Dr. Zachary for talking to us about the fascinating facts of glia cells. Our next speaker is Mr. Ming Chang Liang. Ming Chang is currently a PhD student in cognitive psychology at Stanford University. He will be speaking with us today on motivated perception and how the brain sees what it wants to see. Let's give him a warm welcome.
Sure. Yeah, share the link on Facebook, Twitter. Oh, we have the Twitter. It's better not share my own Facebook.
Hello. First of all, I want to say a big thank you to the organizers for this invitation. This is a marvelous event. I wish I had something like this back in high school, and I'm really honored to be part of this as a speaker. So my talk today will be about perception. In our everyday lives, we often rely on our perception as an objective, accurate representation of the physical world. We do this each time we make judgments on distance, speed, depth, or even more aesthetic qualities such as beauty and sublime. But is our perception as objective as we would like it to be? Or can it be distorted by our desires and wants? At some level, I think this is a phenomenon that everyone in this room has somewhat of an intuitive understanding of. So, for example, imagine we're watching a soccer game, a heated soccer game between two teams. The two teams are tied going into the final minutes, and whoever scores the next goal will likely win the game. At this moment, someone takes a shot, it soars past the goalkeeper, hits the crossbar, and bounces off the goal line. Was that a goal, or was it a near miss? It might depend on who you ask. So this was something similar actually happened in the 1966 World Cup final, for those who follow soccer, when England scored the infamous Wembley goal against West Germany and went on to win their first and only World Cup. But was that a real goal? Well, the English thought so. The Germans were a little bit more skeptical. Let's ask people who were actually on the field that day. So the English player thought that the ball certainly crossed the line, while his German counterpart was equally confident that it did not. But maybe they were looking at it from a different angle. How about people watching the same video on YouTube? Even then, people couldn't seem to agree. So what's going on here? Why is the same visual information giving rise to systematically biased perceptual judgments? One obvious possibility is that, well, one group of people are lying. Another more intriguing hypothesis is that really wanting to see something can make people more likely to see it. So the notion that desires and wants can bias our perception is a fundamental challenge to the objectivity of our perceptual experience. So not surprisingly, it's been a source of intense debate. It's a question that psychologists have been studying for, I would say, 6 decades. So for example, in the classic example from the 50s, 2 professors at Princeton and Dartmouth showed students the same video footage of a rough and dirty football game between the 2 schools. And students consistently found that the other school was more responsible for the dirty play, despite watching the same footage. In more controlled experiments, psychologists have shown participants ambiguous stimuli like these. So this could be a bee or a 13, or a seal or a donkey. And by pairing one of the percepts with reward, participants are more likely to report having seen that percept when presented with the stimuli. Similarly, if you were to show 2 images separately to the 2 eyes, pairing one of those images with reward makes you more likely, makes one of the percepts more likely to be the initially found percept. So overall, there is sort of increasing or at least growing evidence that motivation can affect perception. But on the other hand, these same studies are often criticized on methodological grounds. The criticism also goes back all the way to the 50s and persists to this day. And chief among these concerns, and I suspect this is one that you might already be thinking of right now, is that these experiments, these early experiments might be reflecting, these results might reflect the fact that motivation is affecting what people report seeing and not their actual perceptual experience. That is, it's biasing their responses and not their perception. So, which is it? I don't think I'll be able to resolve a 60-year-old debate in a 20-minute talk. But what I hope I can do is to show that the tools of computational modeling and cognitive neuroscience can add an important and new perspective to this debate. So our approach draws heavily from the experimental framework that has been incredibly successful in studying the neural basis of perceptual decision making. The basic idea is that we'll show participants ambiguous stimuli like these. So these images are created by morphing a face image and a scene image together in different proportions. We have participants make categorical judgments about these images. So do they see more face or more scene in this image? And then we model participants' choices using computational models. You can think of a computational model as representing a hypothesis about the underlying cognitive processes that give rise to a phenomenon, but written in the form of a computer program. And the model makes specific predictions, so we can compare these predictions to participants' data to get a sense of which model best describes participants' behavior. So this is one part. We can also use functional magnetic resonance imaging to measure neural activity as participants look at these stimuli. And the reason that we're using faces and scenes is because we know from earlier work that faces and scenes are processed in different parts of the brain and are represented in distinct patterns of neural activity. So what we can do is to measure this neural activity and try to get a sense of whether motivation biases the neural representation of these images. So basically, what we're trying to do is to not only to examine if motivation biases behavior, but also to decode what participants are actually seeing from brain activity. And finally, we can complete the circle and relate the neural data to the formal models to study the neural implementation of the computational processes described by the model. So these are the stimuli that we show our participants. They're created, as I said, by morphing face and scene images together, and they range from 0% scene and 100% face all the way to 100% scene and 0% face. Participants' task was very simple. They just had to indicate whether they saw more face or more scene in an image, that is, which category was of higher intensity, and then they were rewarded for each correct classification. So the more often they had this correct, the more money they will win from the experiment. But at the beginning, on each trial, at the beginning of each trial, we motivated participants to want to see one category over another. To motivate participants to see more scene, we told them that they will win extra money if the upcoming image had more scene and lose some of their earnings if the upcoming image had more face. To motivate them to see more face, we told them the exact opposite. So did motivating participants to see one category over another bias their perceptual judgments? So let's take a look at the data. So here's a plot of participant psychometric function, which maps the relationship between how much scene there is in an image and participants' responses. So not surprisingly, when there is more scene in an image, participants were more likely to report seeing more scene. This graph is when participants were motivated to see more face. When participants were motivated to see more scene, we see that the curve shifts left, such that for the same face-scene proportion, participants were now more likely to report having to see more scene than face. In other words, the same level of objective evidence, participants were now more likely to report seeing the category that they were motivated to see. You can quantify this bias for each participant, and here larger numbers indicate a stronger motivation bias. And you can see that most, but not all participants were somewhat biased. And this bias comes at a cost, because the more biased you are by what we motivated you to see, the less accurate you are in making your classifications. So participants who were more biased more biased by motivation also earn less from perform worse on the task and earn less from the experiment. And we also replicated these results with an independent group of participants who performed this task outside of the economic scanner. So these results, these behavioral results provide evidence that participants' judgments were biased by what we motivated them to see. But they don't really say very much about how this happens. And to get at this how question, one approach is to use computational models. So the drift diffusion model is a model that's commonly used to study perceptual decision making. In essence, it's a system of equations, but it also has a very easily interpretable graphical representation. So to take you through this, let's assume that perceptual decisions arise from the accumulation of noisy sensory information from the world. So we can model this evidence accumulation process as a diffusion process with a starting point determined by a parameter, z. And at each time point, we assume that participants sample sensory information from the image. And over time, as you accumulate more, I'm not sure if you can see the graph, but as you accumulate more information until it reaches a threshold, you make a decision. And the rate of evidence accumulation can be modeled by a parameter V, or the drift rate, which is determined by the amount of sensory evidence in the image. So when there's a lot seen in the image, V will be highly positive, and the evidence will accumulate very quickly towards the same threshold. So what this model provides us is a computational framework that formalizes how participants make perceptual judgments. We can fit this model to participants' data to estimate the value of these parameters. You can think of this as tweaking the model, tweaking the parameters until you can generate a model that generates predictions that best predict the data. And when we did this, we found two things. Firstly, motivation bias the drift rate, such that the accumulation of sensory evidence was biased in favor of the motivationally consistent category. This is suggestive of a perceptual bias because it assumes that the way that sensory information is processed has been altered. On the other hand, we also found that motivation bias the starting point by pushing it closer towards the threshold of the motivationally consistent category. You can think of this as more of a response bias because it's not changing how evidence is being accumulated, it's just changing the amount of evidence that you need to make a particular judgment. And taken together, these suggest that motivation bias is both responses and perceptual processing. Of course, believing in these results requires you to buy the assumption model, which I'm not, and that's perfectly reasonable. What I to do next is to look into the brain and provide converging neural evidence of this account. So the model makes the prediction that sensory processing is biased by motivation. This is a hypothesis that can test directly by measuring sensory evidence in the brain. So to do that, at the end of the experiment, we show participants images of complete figures and complete scenes. So this is to allow us to measure the level of neural activity in responses to faces and scenes. As I mentioned earlier, we know from earlier work, faces and scenes are represented, so processed in different areas of the brain are represented in different patterns of neural activity. What we can then do is to train a machine learning algorithm to recognize these patterns and then apply this algorithm to the data from the past to measure the level of face-selective and scene-selective activity of each trial. So on each trial, this algorithm outputs the probability that participants are seeing a face or a scene as a function of their neural activity. So essentially, we're trying to decode what we think participants are seeing based on their brain activity. So here's the probability that the algorithm thinks that the participants are seeing a scene as a function of like how much scene there is in the image. Again, not surprisingly, when there is more scene in an image, the classifier, the algorithm thinks that it's more likely that participants will see more scene. So this is a validation that we can actually measure the level of sensory evidence in the brain. So this red graph here is when participants were motivated to see more face. When participants were motivated to see more scene, we see that the level of scene-selected activity, of scene-related neural activity is higher at each level of the sense scene, suggesting to us that motivation is not just biasing behavior, but it's also enhancing the neural representation of the person participants were motivated to see. And we can quantify this neural bias for each participant, see if it relates to the estimates of the bias that we generated from the model. So the model, as you might recall, generates estimates of a bias in starting point and a bias in drift rate. And what I show here in this regression analysis is that the bias in neuronal activity is uniquely related to the bias in drift rate. So participants with stronger neural bias were also participants who had a stronger bias in the drift rate estimated by the computational model. So these results provide converging validity of our use of the computational model, and also converging evidence that motivation biases perceptual processing. So this is the perceptual bias. Is that a neural correlate of a response bias? So for that, we turn to what could be a potential mechanism for a response bias. For this, we turn to a slightly different literature, that of reward and motivation. So we know from quite a bit of work, especially in rodents, that the presence of reward cues are likely to trigger wanting states in animals. And these wanting states are associated with animals working harder and faster for reward. It's been hypothesized that these wanting states, craving, it involves a structure in the brain called the nucleus accumbens. You can think of this as, if you imagine hearing the jingle of an ice cream truck and suddenly craving ice cream, wanting to step out. So this is the brain area that we think might be responsible for this. And when you activate this brain area using drugs, you become more likely to strive for reward. And if you deactivate it using drugs, you become less likely to work towards reward. So with that in mind, with this literature in mind, we asked if the nucleus accumbens could also be involved in biasing responses specifically in our task. And it does. So participants with a stronger nucleus accumbens response were also participants with a stronger bias in their starting point. So we can try to examine this nucleus accumbens response more specifically by looking at how it unfolds over time. So here the solid line plots the activity of the nucleus accumbens where participants make choices that were consistent with what they wanted to see. And the dashed line is when they make choices, the same activity when they make choices that was inconsistent with what they were motivated to see. And this graph over here is the difference between the two. And what you can see is that this surge of nucleus accumbens activity occurs before the image appears, suggesting that what it does, it creates a predisposition to make a particular response. So it's not that it's basically a way of increasing the likelihood of making a response that was consistent with what you were hoping to see. So taken together, turning to our opening question, does motivation bias perception or does it bias response? And the answer, I think, like many of the answers in psychology, it's kind of both. And our results suggest that there is dissociable neuromechanisms and dissociable computational algorithms that are responsible for these bias. Specifically, response bias associated with activity in the nucleus accumbens and the perceptual bias associated with activity in the visual cortex. So I think what our results also highlight is perhaps that there is a different way of approaching this question. So instead of asking a binary yes/no question as to whether motivation biases perception, we can start to ask questions of how. And in doing so, trying to get a more mechanistic account of the effects of motivation on our perception. So, we often say seeing is believing, but what do we make of our beliefs if we can't trust what we see? So with sporting events like the World Cup, it's just fun and games, at least for most of us, it's just fun and games. But there are cases where motivational influences on perception have more dire consequences. And I hope that the work I presented today represents a starting point to begin to explore some of these other processes. This is somewhat of a slightly different forum than I'm usually used to presenting, and I thought I would end with some parting thoughts. And I think, what I wanted to say is that neuroscience is, I hope my work shows that neuroscience is becoming an increasingly interdisciplinary field. I think this is part of what it makes it incredibly exciting. We just look at the lineup today to see how many different levels of analysis that we're working with. And I think what makes it really exciting right now is that we're in a place to ask really fundamental questions of human cognition and have the tools to begin to probe at them. From using physiology to computational modeling to machine learning to really begin to understand the mysteries of the human mind. With that, I just want to say a big thank you to my lab, my advisor, Jimmy Zaki, and the collaborators on this project. Thank you.
Thank you so much for that wonderful talk. It was very fascinating to learn about motivated perception. Next up, I have the honor of introducing Dr. Kaneshiro, who received her PhD from Stanford University's Center for Computer Research in Music and Acoustics. Today, she will be speaking on her research which combines neuroscience, machine learning, and signal processing to study how humans perceive and engage with music, sound, and images. Let's give her a round of applause.
Great. Thank you everyone for being here, and I really want to thank the organizers for putting together such a great event. I'm really excited to be sitting here. So today I'll be talking broadly about auditory neuroscience. So what I'll be doing is first I'll kind of do a deep dive into the current study that I'm working on with some collaborators, and then I'll drop back a little bit and give an overview of my research areas. And I'll finish with my professional path, so the organizer suggested that that might be useful to the people attending this event. So I'll end with that, but I'll just give a little bit of information right now. So I also did not have a conventional neuroscience background. My undergrad degree was in music, and my graduate degrees are in music, technology, and electrical engineering. So those are kind of the approaches through which I'm coming into neuroscience. So to start, I'll just go right into a current study. So this is a study on decoding auditory brainstem responses. And this project actually encompasses two different studies. So the first is the experiment itself. And this is a project that I worked on while I was at the Stanford School of Medicine as a research scientist. So it's a collaboration between the otolaryngology head and neck surgery department at Stanford and University of the Pacific in San Francisco. So this is the experiment part. And then for the actual machine learning code that we use to analyze the data, this is a separate project, which is a toolbox for MEG and EEG classification. And this is a collaboration between CARMA, which is the department where I did my PhD and my postdoc, the Center for the Study of Language and Information at Stanford, and the Stanford Vision and Neurodevelopment Lab in the Stanford Department of Psychology. So the motivation for this study is really coming at the topic from a translational neuroscience angle. So if you're a clinician and you have a patient who was just fitted with a cochlear implant, or say you're working with a small child or even an infant, it's hard sometimes to ask these types of patients to describe what they're hearing, right? So they might be experiencing sound for the first time, it's an altered sensory input, or they might even not be able to talk yet. So in this setting, brain responses are extremely promising. So one reason why this is the case is because brain responses are objective. And by this I mean that they're delivered automatically from our listener. And so you don't need to go through self-report, and the person doesn't need to be able to articulate what they're hearing in words. Brainstem responses, as I'll describe in more detail in just a moment, they're very easy to record, and they're actually already used in clinical use for basic assessment of auditory and brain function. Therefore, our question with this experiment is whether we can take this brainstem response that's already used in the clinic, and can we use it in new ways as a possible means of diagnosing and treating patients who have hearing loss or who are undergoing rehabilitation. So as anyone who works with brain data knows, brain data are very noisy and can be challenging to work with. And on top of that, if you're working with a clinical population, each person will have a different condition, a different perceptual experience. So what we're doing in this study is we're going to be validating our approach first with normal hearing listeners and intact stimuli, because if this doesn't work under intact perception, it's highly doubtful that it would work in more challenging situations. So first, I'll just talk a bit about the auditory brainstem response. So this is a very early auditory response. This is something that happens before your cortex actually starts responding. It's easy to measure, so we measure this non-invasively. There's just a single electrode that we put on the forehead, and that will record our response for us. And when I say early response, this is beginning just milliseconds after the onset of the sound. And this onset response will have characteristic peaks that are very easy to see. So in this figure here, we have these numbered peaks, And if you can see the labeling on the x-axis, these are all occurring within the first 10 milliseconds after sound onset. Another interesting characteristic of brainstem responses is that after the onset response, if your sound is sustained, the brainstem response will also be sustained, and it will directly encode the stimulus. So what does this mean? This means that if you play a sound, the brainstem response is actually oscillating at the same frequency as that sound, and it's phase locked to the sound. So this means that if we have enough responses, we can actually kind of play back the sound from the response. I have a couple of sounds here. I apologize in advance if it's too loud.
Me,
Okay, so that's a stimulus.
me,
So do you hear how the pitch of it goes up a little bit over time? I'll play one more time.
me,
Okay, and then here is the average response, or many thousands of average responses to that sound. I know, it doesn't sound very nice. So despite the lower quality, you can kind of still hear that rising pitch contour. So this is a very fascinating response to me because it's actually encoding the sound. So brainstem response is one side of the project. The other side is brain decoding. So as was mentioned in the previous talk, in a decoding situation, what we want to do is we want to make some kind of prediction about the stimulus from the brain response, and we'll use machine learning to do this. So some questions you might ask in a decoding situation, one could be which stimulus produced this response. Other questions you could ask, you could actually ask questions about your participant. So auditory brainstem responses are known to be more robust, so bigger and more resistant to noise in trained musicians, as well as in people who speak tone languages like Mandarin or Thai. So perhaps you could take a collection of brainstem responses and try to predict whether the listener had musical training or not. What we're doing here is called a classification task. So basically, we're building a statistical model from labeled brain data, and then we'll pass new data through that model, and the model will try to predict a category label based on the response. So other types of machine learning tasks that you could do, but we're not doing here, would be to predict a continuous response. So say you wanted to predict number of years of musical training and not just are they trained or not. Other studies actually aim to reconstruct the stimulus from the brain response, but we'll do classification today. So for our experimental design, we have 6 stimuli. They're all very short. They're 135 milliseconds in length. We have 3 speech stimuli, and then we have 3 music stimuli. So I'll play all 6 of them.
ba, da, di,
Okay, so when you listen to them, did you notice how they were all the same pitch? So if you were singing them, you would always be singing the same note. So we did this, in fact, because the brain response is oscillating at the frequency of the stimulus. So we thought it would be too easy to just input sounds with different pitches because then you could classify in that. So what we're doing is we're going to force our classifier to rely on those other cues that enable us perceptually to tell those 6 sounds apart from each other. So we have our stimulus set. I'm sorry I didn't have a picture of a real participant, but the participant comes in, single channel recording. We actually are using a clinical system to collect our data, and our stimuli also come from a clinical system since we're aiming for clinical application. And what you end up with is many, many responses. So for this study, we actually have each participant listen to each sound 2,500 times. And I know it sounds horrible, but one nice thing about this response is that it's such a low-level response that you can basically just play the stimuli one after another, and you don't have to worry about longer effects in the response, which is the case with cortical studies. So after we have our responses, then we bring in the classification software. So what we're doing here is we're taking our data and we're iteratively using some of the data to train our statistical model, and then we'll pass the rest of our data through that model and the model will try to predict which stimulus the person was hearing just based on the brain response. So for this study, we had 13 participants and 2,500 responses per stimulus per participant. Although due to the limitations of our system, we could only export the responses in averages of 100. So it's not exactly single trial classification, but the averaging does help a little bit because it helps to denoise the data. So we're getting added signal quality from this. And since we had 6 stimuli, this is a 6-class classification problem. And this means that if our classifier did not work at all and was just picking things by chance, our accuracy would be around 16.67%, which is 1/6. So what's happening here is our classifier has been trained, it's seeing a response, and then it has to choose between these 6 labels. And so, for instance, it would see this one and say, oh, I think that's piano. So that's kind of like one classification attempt. So when we do the classification in the 100 response averages, we get a classification accuracy over 60%. So this is really promising. It's well above chance level and it's statistically significant. If we average the data further into groups of 500 responses, our classification accuracy is even better. So now we're over 70% 6-class problem. So this is very promising if we want to keep exploring this as a possible clinical application. So when people talk about machine learning and classification, people are often very focused on the overall accuracy, which is what I reported in the previous slide. And it is important for this line of research that the classifier function correctly and that we are able to decode brain responses. However, it can also be interesting to look into the mistakes that the classifier is making. And the reason for this is that they might actually be perceptually relevant mistakes. So if you think about experiencing 2 stimuli that are very similar, you would expect the brain responses to also be similar. So maybe the classifier can't tell the difference between them as well. And we found that this was actually the case. So what we can do is we can take the output of our classifier, and the form of this is called the confusion matrix. I don't have it on here, but basically it's showing all of the correct and incorrect classification attempts. And we can take that confusion matrix and visualize it in such a way that we can see all of the distances between our stimuli. So I'm sorry the font is so small, but on the x-axis are our stimuli. So we have ba, da, tuba, D, piano, and bassoon. And on the y-axis is the distance measure. So the way to interpret this plot is that the distance between any 2 stimulus categories is the height that you have to go up the tree in order to get from one to the other. So based on this interpretation, most of our stimuli are fairly distant from one another, but on the very left, we see that ba and da actually have a small distance. So what this means is that the classifier was having a really hard time decoding responses to those 2 stimuli. And this is actually exactly what we wanted to see. So we selected the ba and the da because they're acoustically identical in the ah part. So it was actually the same signal, and only the b and the d were different. So this is actually kind of validating something that we thought would happen with perceptual similarity being reflected in the output of the classifier. And in fact, if we only look at the other categories, they were all classifying it over 80% in the 6-class problem. So to conclude for this study, we were examining the feasibility of using auditory brainstem response classification for clinical use. To move toward this goal, we used a clinical platform to present the stimuli, also from where the stimuli came, and we collected data on that same platform. We used a publicly available EEG classification toolbox. So this is kind of a later point if we think about clinicians or people who don't have machine learning experts on the research team. We're developing this toolbox with the hope that it can encourage more people to use classification with their EEG data. So for future work, we want to refine our analyses of course, try to improve our accuracy, but also see if we can get this working in a way that requires less data. So for an experiment, this was not too bad. It was about 2 hours per participant. But if you're in the clinic for a visit, you can't sit there for 2 hours and have your brainstem responses recorded. So we're finding the design is one thing. Our next step is to keep using normal hearing participants, but actually alter the stimuli so that we're simulating hearing loss, but still giving a consistent experience across our participants. And finally, this approach may be very promising for looking at effects of training and learning. So as you adapt to a device, perhaps your adaptation will show up first in your brain response, like even before your behavior catches up. So we think this is a very interesting line of research using EEG classification. So now I'm going to take a step back and just give an overview of other types of research that I'm working on that have to do with the brain and also not to do with the brain. So what I talked about already was EEG classification. So here we're using machine learning with brain responses to assess perception, also look at similarities among stimuli. And so the question here is whether we can correctly predict which stimulus was being experienced just based on the brain response. And so the study that I presented today was with auditory brainstem responses and 6 stimuli. With my colleagues at Stanford, we've also looked at cortical responses to musical events. And to me, this is where things get really interesting because now it's not just about decoding the processing of the sound itself, but how it's functioning in a musical context. So what we did is we took a set of musical events, so chords, and we put them in context where they would be expected or unexpected. So when we do this analysis, you can actually have the same musical event, but we can classify responses to that event successfully just depending on whether it was an expected event in a context or an unexpected event. So now we're actually getting beyond just processing of the stimulus itself, but how we are perceiving it and how it's feeding into our musical expectation formation. In another study, this was a vision study, we did a classification of cortical responses to 72 images. So in this one, we had these 72 images that fell into categories of different levels. So at a high level, we had animate and inanimate, and then within each category, we have things like body, face, and human animal. And I think following up from the previous talk, when we do a 72 classification and look at the confusions, we found that responses were tending to cluster according to what category they belong to. So human faces have a very distinct response in cortex. So using EEG, we found that the human faces would form a big cluster. So that means that their responses were being confused a lot. Animal faces were forming another cluster. Responses to human hands were tending to be confused with each other a lot. So they were also forming a category cluster. So I think this is one of the really exciting directions that classification studies can go in, because you can start looking at these really large stimulus sets and looking at how they're represented and how their similarity structure emerges just through the brain response. My other main focus of neuroscience research has to do with neural processing of real-world music. And so the goal here is all about ecological validity. So in the study I talked about previously, we had stimuli like DAW. And this DAW is actually kind of a famous stimulus if you do auditory brainstem research. It's used in a lot of studies. It's a wonderful stimulus, and I'm glad I got to study it. But how do you go from studying a response to something like DAW to studying a response to something that's on the Billboard charts right now, which I think is also a valid and important question. And so in my other line of research, we're actually going to the complete opposite end of the spectrum and looking at stimuli like this that are complex and also complete. So by complex, I mean you can no longer just parametrically alter small features of the stimulus because it's a real world piece of music. And by complete, I mean that maybe we want people to actually listen to the whole song. So now we're working with stimuli that are 1 minute long or 4 minutes long, or even 8 minutes long. So to do this, we go not to the brainstem, but to cortical responses. So in this figure here, some of you might be familiar with, this is the more commonly used EEG recording paradigm. So on the left, we have an electrode net. So instead of the one electrode for brainstem, we now have an array of, this one has 128 electrodes. And so what will happen is that each of those electrodes will record their own time series of data. So now you're working with a matrix of data, and if your stimulus is several minutes long, this data matrix can also become quite large. So in addition to complexity on the stimulus side, we have more complex and noisy cortical data. So this turns into kind of an interesting signal processing problem to be looking at these types of responses. So with my collaborators at Stanford and at City College of New York, we're doing a few different approaches to start looking at this natural music processing. So one way that we're looking at it is to look at the synchrony of responses across listeners. So if you imagine a setting where you have 20 people listen to the same piece of music, what you can do is you can look among those responses and see what types of brain activity are reliably evoked across all of your audience members. So this is an especially important approach because the stimuli are complex, so you don't necessarily know what you're supposed to look for in the brain response. So this approach kind of lifts that requirement because you don't need to know what to look for, but you're just looking for what is evoked reliably across your audience. A second approach is where instead of looking between people's responses, we can actually try to link the response to some stimulus feature in time. So you can do computationally extracted features from your stimulus, so something like amplitude envelope, or maybe some kind of spectral feature that varies over time with the same temporal resolution as your EEG. And what we're finding is that we can uncover significant correlations between the EEG response and these stimulus features. And that the degree of correlation depends on things like the acoustical quality of the music, the interestingness of the music. And in fact, these two types of responses kind of tell the same story. So we're finding that when something very important is coming up in the music and there's a sense of expectation, again, people's brain responses will become more synchronized and also track stimulus features more. A third area that we're looking at with natural music has to do with neural oscillations at the beat. So if you listen to a piece of music that has like a steady beat, your brain is actually, or your neural oscillations are actually oscillating at the same frequency as the beat. So that might sound obvious, but I think it's actually really interesting. And it's been studied a lot with simple rhythms. But when you go from that to the complexity of real world music has activity going on at all kinds of frequencies, not just the beat frequency. So the fact that our brains are able to lock on to those perceptually relevant beat frequencies and have such a prominent oscillatory activity at those frequencies, I think is really exciting. I also do research that doesn't have to do with neuroscience. So I'm broadly interested in musical engagement. And so some other research that I work on has to do with getting out of the lab and looking at real world data. So for example, with my colleagues at Stanford and Shazam, we did a study on when people actually Shazam songs. Does everyone know what Shazam is? So if there's a song that's playing on the radio and you don't know what it is, it's an app that you can use and it'll listen to the song and tell you what song it is. So what we did is we actually looked at when people were performing that query, and we had some interesting insights having to do with choruses and vocals and whether the song had just come out or whether it had already become very successful. So some good engagement insights there. We've also looked at reuse of song lyrics over time using a large corpus of industrial data. And something I'm working with a student on now has to do with technology and collaboration with music. So if you think about recommendation systems and things like that today, it seems to be moving in the direction of making everything very hyper-personalized to you. But then the question is, what does that do to our social experience of music? Because music has historically been a social activity, and it's becoming more and more a single listener event. My last area of research is kind of about neuroscience, I guess, but it's all about software and data sets. So the goal here is to make our own research more transparent, but also facilitate research for others. So this is actually a trend in neuroscience already. So those of you who are interested in neuroscience, I'm sure will encounter this in your studies. But more broadly, we're thinking beyond just the single field and how doing things like this might help cross-disciplinary insights move multiple fields forward. So the EEG classification toolbox I mentioned earlier is one example of this. We also have several EEG data sets that are publicly available. We have a toolbox for creating auditory experiments. So the actual act of loading a stimulus and playing it and collecting responses can turn out to be more tricky than you'd expect. And the Shazam study, we published Shazam data, and we have other things too. So this is just an example of a tapping data set that we released. So we had people tap out the melody to Hey Jude. So if you look at the plot, you might be able to see the melodic contour of Hey Jude by the Beatles. But the main point here is that we think this is important because not everyone has the necessary skills to do what they want. Not everyone has the necessary access to materials to do what they want. So if you're a cognitive neuroscientist who doesn't know that much about machine learning but wants to try it out, we hope that our classification toolbox will be useful to get someone started. Or if you're a machine learning researcher who doesn't have access to a neuroscience lab, perhaps you could work with one of these EEG data sets, and perhaps you would arrive at some insight that would ultimately benefit people in other fields. So when we have publications now, we try to release the data and the analysis code as much as possible. So to conclude, I'll just talk a little bit about my professional path. So as I said, I don't have any degrees in neuroscience proper or in psychology. So I did all of my schooling at Stanford. I started out as a music major, and if you had asked me or told me then that I would be talking about neuroscience one day, I would just be like, no, that's not going to happen. So I did my undergrad in music. I worked for a little while. I went back to Stanford for graduate school, and so I did a master's and a PhD at CARMA, which is the Center for Computer Research in Music and Acoustics. And I later did a postdoc there. And while I was there, along with my PhD advisor, Jonathan Berger, we formed the Music Engagement Research Initiative, which is an interdisciplinary research group in the department. And it kind of broadly encompasses all of the topics I've been talking about, and even additional topics too. While I was in graduate school, I also completed an engineering degree, and I'll say that this engineering degree was actually the key component of my education that enabled me to do the type of neuroscience that I was interested in. So this is where all of the machine learning and all of the signal processing background came in and gave me the tools that I could use to look at auditory processing and music neuroscience in new ways. Following my postdoc, I also worked as a research scientist in the Stanford School of Medicine. So my non-neuroscience research falls mostly under a field called music information retrieval. So this is a field that looks at computational analyses of music. And if you think of companies like Pandora and Spotify, like those are kind of core companies of this field. So through my work in that field, I've also had the privilege of working at Shazam and working at Smule, and I'm active in the International Society for Music Information Retrieval and the Women in Music Information Retrieval community. So to close things out, I thought I would just give a few perspectives that I've gained over the past decade or so. Maybe they'll be helpful to you. I mean, this has already been mentioned today, and I think it's fairly obvious just from the range of speakers, but neuroscience can be approached from so many different angles. So for me, it was music and audio and also engineering. But I would encourage all of you, if you're interested in neuroscience, to just don't fall into the thinking that there's like one way to do neuroscience or one path that you're supposed to pursue. And maybe just see, you know, what aspect of it aligns with your interests and see what's going on in that subfield of neuroscience, because something probably is. Also, the field is always changing. So the methods that I'm working with today, over half of them didn't exist when I started out. So I would say to just don't feel like you have to know right now what you want to work on forever, because the thing that will really get you in the end might not be around yet, or maybe you'll be the one to help it come around. Make and maintain connections. So for me, the most interesting influences on my research have come from people who were not working directly in my field of research. So for me, working with vision researchers and working with bioengineering researchers, and taking their approaches and translating them over to the field of auditory and music neuroscience, that actually brought about the most innovative aspects of what I'm working on. Find mentors. So I was a first-gen college student, and I didn't know this was so important until well into graduate school. So find mentors. It might not be the people that you think are supposed to be your mentors. So it might not be the prestigious professor with the huge lab. It might be a postdoc, or it might be a grad student. But I would say that it's really critical, especially in this field, to have someone who's looking out for you and who's going to support you as you move forward. And I would also say that you probably won't find one mentor who can do all of the mentoring things for you. So maybe think about finding multiple mentors that you can consult with and learn from. And finally, I would just say to explore and be uncomfortable. Maybe try something out that's not exactly what you think you're supposed to be doing. Try something that you won't be good at, and I think sometimes that will turn into really exciting opportunities that you can't anticipate in advance. So that's the end of my talk. If you're interested in any of the projects I was talking about, there are papers linked on my website. I'm happy to answer questions over email. And I just wanted to thank all of the funding that supported me during grad school and beyond. Thank you.
Thank you so much, Dr. Kaneshiro, for your enlightening presentation, especially those perspectives and little pieces of advice at the end. We're going to be taking a 15-minute intermission. There's lots of free food in the back. And we're going to be done at around 2:50 with the intermission. So see you all in 10 minutes. Enjoy the food and water.
If it's live on YouTube. I know, I posted it. Go you. Okay.
Is there a difference between the yellow one and the blue one?
That's what I'm thinking. Yeah. They both say it's all
I think they're the same.
in the back. Maybe they don't.
Can't really tell.
They both.
Yeah, exactly. Both of them. Sorry.
What's up, man? Oh, you know who Alan is?
Yeah.
Oh, dang.
What about him? He's okay.
Yeah. I think that's like really good.
That's so cool.
Chocolate onion pie.
Oh, like.
Past president. If you want this
Should I get these Doritos or should I get?
Yeah, that sounds like I was grabbing. Oh, they have nachos.
I want the Doritos. I love Doritos.
Which one should I get?
Sun chips.
Huh?
Sun chips.
I don't really like
Or should I get pretzels?
pretzels. They're not.
I'm gonna get Doritos.
Okay, we're ready guys. Okay, so he's really good. I want to make you guys Did I talk to you guys already? Yeah, you okay. Anyway, so I started something where you guys me or another so you can email me at the one at the bottom. Yeah.
Wow, we really downed these chips.
So
We have more, right? Yeah. The back? Well, I mean, it's too late.
Yeah, so this is so just email me and I'll send you a picture of them or the guys. I'll just candy. I was like, I'll set you up. So it'll be people. I was like, there's literally a tear. Where are you? Okay, so there's people able to come up to Palo No. Wait, oh. You're like no to her. I was like, oh no. Damn. That's hard. Email me and I will try my best to get set up with the YMCA. So yeah, for sure email me.
I don't. No, there's no more legs. I'll take this.
I will come.
Sorry.
They ran out so quickly. What the heck?
I feel so fat, dude. Oh, hello. We're live.
I'm so ugly.
I just
Contest of I'm wondering.
I was wondering if there's like access to the slides.
This is my second bag.
No.
No.
There's like no.
I'm kidding. Like my little. Ooh, so I'm sorry.